Look closely at this tower. It is a real structure, rising from the desert one floor at a time. But compared with its intended height, it is still less than halfway there. Jeddah Tower is designed to rise beyond 1 kilometer. Yet every new floor makes old problems harder. What fails first when a tower keeps getting taller? The wind, the ground, the construction process, or the building's ability to function? Before answering, we need to separate two versions of Jeddah Tower. One is under construction. The other is this planned concept. Its architect describes a design exceeding 1,000 meters. That is a target, not a completed or guaranteed height. We are watching them solve a moving chain of problems. Start with the force that makes the tower change its shape. Imagine replacing Jeddah Tower with a simple rectangular tower of the same height. Wind would not push it once and disappear. Air can separate from alternating sides. The wind can pulse from one side, then the other. Engineers call this vortex shedding. A rectangle gives that pattern a consistent target. Jeddah Tower takes a different approach. From above, its footprint spreads into 3 petals. The wings taper as they rise, so the outline keeps changing. The architect describes this form as helping reduce structural loading associated with vortex shedding. The petals do not eliminate wind. They change the shape the wind sees. Instead of waiting for weaker wind, the building changes the object the wind must push, but its weight still has to go somewhere. Look at the tower from the side, and it seems to end at ground level. Structurally, it does not. Every floor adds weight. That weight travels through the walls and vertical structure, down into the foundation, and finally into the soil. Wind pushes sideways through the same system. Thornton Tomasetti describes interconnected concrete walls resisting both gravity and wind loads. Those walls are part of the building's skeleton. Below them, the planned foundation is described as a 5-meter thick raft supported by 270 deep concrete piles. Each is listed as 1.8 meters wide and up to 105 meters deep. Those numbers reveal scale. The tower's height does not stop at the pavement. It continues through the raft and deep into the ground. A kilometer-high structure needs one complete path from its highest floor to the soil below. There's another version of the tower that engineers must solve, the unfinished one. During construction, the final load path may not exist yet. Some walls are present. Some floors are incomplete. Equipment and access routes move as the tower rises. On April 20th, 2026, Thornton Tomasetti reported that Jeddah Tower had reached 100 floors and 400 meters. On June 18th, it reported that the tower was nearing its 104th floor. These are dated milestones, not today's status. But each stage faces the same question. What is holding everything up right now? It is also a vertical supply chain. Concrete, reinforcement, workers, and inspectors move through a changing site. Material arrives. It is placed. The work is checked. The next floor begins. The difficult part is repeating that cycle without allowing small mistakes to travel upward with it. At extreme height, construction becomes a control problem. Routes, measurements, and checks must rise with the tower. From outside, height is an impressive number. From inside, height becomes a daily journey. The architect's project description lists 59 planned elevators, 54 single-deck, and 5 double-deck. Observatory elevators are described at a planned 10 meters per second in both directions. The same design places a planned sky terrace at level 157, approximately 30 meters across, for public use. But every shaft and mechanical route takes space. The systems that make the height usable also consume part of the building. The taller it becomes, the more infrastructure it needs, leaving less floor area for ordinary use. A tower can succeed structurally and still become difficult to use. That brings us to the final threat. A tower this tall does not behave like a rigid ruler. Wind can move it. Heat expands materials. Tiny construction errors shift connections. The movement may be small. The consequences are not. Elevators still need usable shafts. Facade connections, pipes, and floor finishes still have to meet. So the goal is not zero movement. The goal is controlled movement that keeps the tower usable. This changes what strong means. A structure can remain standing and still fail as a building. People may feel uncomfortable. Elevators may become harder to operate. Connections may become harder to maintain. For a 1-kilometer tower, standing is only the beginning. It must move without losing its ability to connect, transport, and function. Return to the tower rising from the desert. The construction footage shows the problem in progress. The concept image shows the intended destination. The pedals change the wind problem. The walls carry forces into the ground. Construction controls the route upward. Elevators turn height into transportation. Controlled movement keeps systems connected. The engineering answer is clear. You do not build beyond 1 kilometer by making one part impossibly strong. You build it by making wind, gravity, ground, construction, movement, and daily life agree on the same building. Not one miracle. Coordination at the edge of failure. If you want more stories about how impossible structures work, fail, and survive, subscribe to Inside the Impossible.